It's in series.
So let's talk about problem number 2. And actually, this is kind of a historical thing as well. So if you look at how what used to be called the incandescent light bulb, which is horribly inefficient. So basically what would happen, and Thomas Edison was the first one to come up with the process, and the difficulty wasn't the concept of you force electric current through a high resistance and it heats up. That wasn't the problem. It was how do you commercially produce it, and then how do you make a vacuum inside the bulb so that it doesn't automatically ignite the oxygen and basically start a fire. So that was part of the problem. So how incandescent bulbs as opposed to LED lights, and this is why everybody's shifting to LED lights, because LED lights have, which stands for light emitting diodes, consume a lot less electricity than the old incandescent bulbs do. So how the incandescent bulbs used to do, this was like the ultimate smash mouth physics. So you would take a very high voltage and you would run that current through a small filament, it's a very small wire. And we'll get into this later, but the smaller the cross section of the wire is, the higher the resistance is. So you would feed this current in, and then it would go through this very, very small wire, which had a very, very high amount of resistance. And so that wire would get so hot that it would begin to emit photons in the visible light spectrum, okay? But unfortunately, that wasn't very efficient because of the fact that the only way you could make this work is to waste so much of that energy as a byproduct of a production of heat. So it wasn't just, oh, let's just make light. You're producing a tremendous amount of heat with it because this has so much resistance. So then it's like and I was explaining this to Lauren last night, you can make the analogy of walking down the hallway, okay? So if the hallway is very crowded and you're trying to get through there, you're going to run into a lot of people and you're going to jostle around. So what happens to create that resistance, and this is going to play out today, when you narrow that hallway, that increases the resistance because of the fact that it's harder to get through there, so you're going to be running into more people. But with that said, let's talk about problem number 2. The whole key to problem number 2 is that it's all connected. So since it's all connected, the current on one side has to equal the current coming out on the other side because it's just one complete circuit, okay? There's no branches, it's all in series. So in that situation, the thickness of the wire doesn't matter, okay? What would matter is if you had 2 completely separate wires and you were trying to get a current to go through them, the one that's smaller would have a much higher resistance than the one that's bigger. It's just like a hallway. So if you've got a big open hallway, you don't run into a lot of people and you don't have much resistance. You narrow that down, you're going to run into a lot more people and your resistance is going to go up. So that answer on, I think it's 3, no, it's number 4. The light bulb is connected to a battery. So in both of those, that's just going to be the same because of the fact that it's going to be the same current going through it because it's all the same circuit. Okay? If they were separate, which we'll deal with today, that's a whole different thing. Okay, when you get to, I think it's number 12, which is like Kirchhoff's rule. So, and 11 is kind of the same thing. So here's the whole idea, like on number 12, you've got 5 amps coming in. Now, when you talk about amps, which is a measure of current, so the simplest way to calculate current, and there's a whole bunch of different ways to calculate current, is charge per unit of time, which means that's going to be coulombs per second. What you have to watch are the units. So if you look on problem number 2 up above. You got 2 times 10 to the 13th electrons flow through a transistor in 1, and you got 1.0 ms. What does the ms stand for? Milliseconds, okay? You have to watch those prefixes. So that's going to be milliseconds. Now, you have the number of electrons. How much charge is on each electron? Yeah, just, well, 1.6. Don't worry about the negative signs. Just 1.6 times 10 to the negative 19. Yeah, it's a negative value because we're just after the number. So, your answer to number 2, by the way, it would make a GPA times 10 to the negative 30. Okay? Not horrible, not bad, just 10 to the negative 30. So, when you get down to this question with the 5 amps flowing into this thing, so it's just like conservation of energy, the amount of energy has to stay the same. It's like conservation of amps. The total amount of amps has to stay the same. So if you have 5 amps coming in, at any point, everything has to add up to the 5 amps. So it's just how are you going to split it? So just make sure everything adds up to 5. Now, I know on number 11, if you look in the back of the book, it gives you like a negative 2 amps, okay? Which makes no sense whatsoever. Why there's a negative sign there is stupid, okay? It's just make everything add up to 7, okay? Don't flip out and go, oh, it's negative 2. No, negative 2 amps doesn't make any sense at all, okay? Why there's a negative sign there, it shouldn't be. So if you have negative 2 amps, don't. It's just bad. Anyway, so when you get to question number 14, and this is just terminology, because electricians can't get their Scooby snacks together. So when it says, what is the EMF of a battery? EMF just stands for electromotive force, which is the same thing as voltage. So EMF and voltage mean the same thing, okay? Which I've mentioned before, but in case you've forgotten, okay? So EMF just means voltage. And that's the whole point. So whether it's a battery, whether you plug it into a wall, whatever, we're mostly going to work with batteries. So the whole point of a battery is that you have, and again, if you want to think of this analogy of little electrons and they're walking in and they're carrying like a lunch pail, okay? And when they leave the battery, their lunch pail is full of Scooby snacks and M&Ms and Twinkies or whatever food that you need. And then they're going to go out and they're going to do work, or maybe they're going to hit a light bulb and they're going to have to force their way through that. And when they force their way through that, they eat all their food, and then it's like, oh my God, my lunch box is empty. Well, what am I going to do? Oh, I'm going to go back to the battery and get more food. So you can think of the battery as being like the kitchen where the electrons come through and they get their lunch pail filled again. And eventually we'll talk about whether your mom cooks in series or cooks in parallel. No, it's true. We'll explain that. It's how your mom cooks. So it has to do with resistance and a whole bunch of other things.
Protection lines.
So anyway, so your answer to number 14 should be around 14. Around. Around.
Miss this so much.
Your answer to number 6 should be something times 10 to the 4th.
6.
Okay.
Yeah, your answer to number 6 should be something times 10 to the 4th.
You know, I need.
Okay, any questions on that? Should have been fairly straightforward.
You know, I should erase these and put.
Going once, going twice, make sure you two don't have any stupid mathematical answers.
No.
Is 5 plus 2 7?
I refuse to
is
answer
that?
that question.
That's what you gotta calculate for.
You're right. Oracle, speak wisdom. Yes, it's spoken wisdom. There you go. It says it's 0.7.
I had a C there for some reason, so I just wanted to check.
Yeah, that's this many.
I feel like 50 divided by 7. It's still easy. At least for now.
These how do we have? Was one of the for alcohol. Oh, this is what he's what causes the electrons to move through
I'm never gonna stay. I'm never gonna stay in this class.
Yeah, it seems to like people now know just to wait until I say excuse me and then you.
We left before the bad guy.
Yeah. I never say excuse me after I get what I've done station.
There you go.
The only piece of field is just flowing.
Yeah, it's just the
electrons to the blizzard gate.
Oh,
It's in the book. It's in the book.
You guys moving
the
the
book.
You're like
One
that.
beginning.
You're like that first round of battery creates an electric field because look at the cars started to
Help. I'm being harassed. It's his fault.
Okay, before I forget, if you've been in my AV chemistry class, you've already heard this, but for May South Elementary, you kind of heard what we did at the other night when we had like the open house. So they reached out and said, hey, would your kids be willing to come down and do the same types of thing at May South? So it's not going to be for a while, it's like April 15th. But it'd be the same type of gig. So again, if you're looking for service hours, if you just kind of want to, make kids excited about science, that would be that opportunity. So don't have to worry about it now. It's just kind of planting that seed. If you want to begin to work around your calendar, I think it's like on a Tuesday night. So anyway, just think about that. All right. So let's talk about some different equations today, and a lot of this is going to focus on resistance. So if you look at kind of like one of the major equations in all of study of electricity and physics in general, most people just refer to it as VERT, okay? Voltage equals current times resistance. Your equation sheet gives it as I equals V over R. Why they make it complicated, I don't know. That's just how they chose to solve it, but that's what it is. So when you look at how this is going to play out mathematically, and I'll go back and I'll show you some demonstrations here in just a second. So typically, your resistance is measured in something called ohms, okay? And that's shown by the uppercase omega. So like it might be like a 10 ohm resistor. So that's what we're going to use in the demonstration here in just a second. That's a 10 ohm resistor. So even though it's measured in ohms, it's weird, like we don't put OHM. It's the only time, or one of the very few instances where you say ohms, it is kind of a chant thing, like ohm, okay? But we use a Greek letter on the end of it instead of, so it's just weird, but it's just the hand that we're dealt. So the bigger that number is, all that means is that it's harder to get an electric current to go through it. So like back there, I've got like 1,000 ohm resistor, which is really, really big, which means it's really, really, really difficult to get electricity to flow through it. So I is just your current. So, and voltage is just how much energy there is. So here's kind of a way that you can view this. So if you view this in terms of being a dam, okay? And voltage is going to be like the height of the water. So the higher that water is stacked up behind the dam, the more energy that it has to do work. Okay, so the height of the water column, that's like your voltage. Okay, cool, there's your voltage. Your current is determined by the flow rate of the water. So here's kind of the classic example with this. So imagine that you have this big massive dam. And you have two situations. Situation number one, you have this really long straw that the water can flow through. Okay? It's a really long straw going from the top of the dam down. Okay? And right beside it, you have this big, massive concrete tube. So you have one, which is this really small straw, and beside it, you've got the big, massive tube. Which one has the higher voltage? The straw or the big, massive concrete tube, or is it just the same?
It's the same.
It's just going to be the same, because they both have the same potential for that water to flow through it. Okay? So in both situations, you're going to have the same voltage. All right? Now, if you look at this in terms of current, which one's going to have the bigger current? The one with the big open pipe or the straw?
The
Big
big
pipe.
pipe.
Big open pipe, right? Because it's going to be easier for that water to flow through. So the big open pipe is going to have a big current. Well, if that has a big current, what do you know about the resistance?
Low.
Yeah, then you're going to have a small resistance. Because it's such a big pipe, it's easy for that water to flow through it. Okay, cool. Now, and you can make this analogy in this situation, like you're trying to get out of the parking lot or out to get out of the parking lot. Oh, okay, if I let you guys out 5 minutes early every day, oh, hey, that's simple. The hallway is big, open. You're not going to have a lot of resistance, and there's going to be a big outflow of my AP Physics students out the door because there's going to be a big current because there's very little resistance. Because you all was like, oh, it's Thursday afternoon, it's nice outside, we really want to get out to your cars. So your desire to get to your cars is like the voltage, okay? The resistance is how many kids you're going to run into, and the current is how many of you are going out the door at a given amount of time. Makes sense. Now, situation number two, you've got your little straw. How much water is going to flow through that little straw?
A lot less.
Lot less. So that's going to have a much smaller current. So the only way that you can make that happen then is if what's going to happen?
Big resistance.
You've got a big resistance. So the smaller it is, and that would play out when I let you all out. I was like, hey, no, I'm not done with my lecture. I'm going to be a jerk. I'm going to make you all stay 2 minutes after the bell rings because I'm still pontificating. So if that's the situation, the hallways are going to be very crowded. You're going to have a narrower space to get through. What's going to happen to your resistance?
It increases.
It's going to go up. Now, and this is like a light bulb. Your resistance is going to go up. You're going to start jostling into people. It's like, oh, your blood pressure is going to go up. Your temperature is going to go up. God, Burkamp's a jerk. He made us stay after school. I know he wanted to get out of our car. Okay? And you're going to start emitting bad words or light or photons or whatever you want to think of because of the fact that your resistance has gone up. So, in both situations, you have the same desire to get out to your car. It's just a function of resistance and current. Okay. So, that's one way to look at it. So let's go to the back. Danny, bring you onto camera, and let's go take a guess.